Welcome to EDU World Space.
Chapter 4, Problem 39, deals with a basketball player with an impressive vertical leap of 1.2 meters. Part A wants to know how fast was the basketball player moving when his feet left the ground. So we're going to say V final up here is 0 meters per second because he momentarily comes to rest at the very top of his jump. We're going to go ahead and use a kinematic equation here, and we're using this one. V final squared equals V naught squared plus 2 times A times delta y being the height that they reach. So we're solving for V initial, so V final squared minus 2 times A times delta y is equal to V naught squared. And we're going to take the square root of that whole thing to get rid of the square on the other side. So plugging in our values here, V final squared was 0 minus 2. Now it looks like we're going to get a negative under a square root, but remember the acceleration due to gravity is negative 9.8, and our height is 1.2 meters. So after we plug all that lovely stuff in, we end up with an initial speed of 4.85 meters per second. That is his speed when he leaves the ground. Now part B says if the basketball player is pushing off the ground for a total of 0.3 seconds, what is his acceleration? So acceleration is the change in velocity over time. So this is just while the basketball player is pushing on the ground, in contact with the ground. So this doesn't actually have to do with when he's in the air, because he can't push on the ground when he's in the air. So the change in velocity is 4.85, because he starts from 0, reaches 4.85 the instant he leaves the ground, and the time they tell us is 0.3 seconds. So putting that into the handy dandy calculator, we end up with 16.2 meters per second squared for the acceleration of the basketball player. Now part C wants to know what force does the basketball player push on the ground with. Really what they're asking for is, if we look at a free body diagram of the basketball player while he's jumping, while he's accelerating off the ground, then we are looking at, yes, mg for the player, but we are looking at a large normal force going up. This player is accelerating upward while they're pushing on the ground. And so that means the normal force needs to be bigger than mg. So if the player pushes on the ground pushes on the player. That's that normal force we're talking about here. So really, we're looking at the normal force, and we go to Newton's second law to do it. The net force in the y direction is equal to m times a in the y direction. What was the acceleration in the y direction? We just found it, 16.2 meters per second squared. So we have the normal force going up, it's positive. mg going down, it's negative. That's equal to ma in the y direction. Solving for the normal force then, it's going to be ma plus mg. Oh, and they were tricky with us. They gave us the weight of the player, not the mass of the player. So we do need to find out what his mass is, dividing that 890 newtons by g. He's got a mass of 90.8 kilograms. So let's go ahead and plug all this stuff in. 90.8 times 16.2 plus 90.8 times 9.8. And we end up with a normal force equal to 2,360 newtons. Quite large. That's the force the floor pushes on the player with. That's also the force that the player pushes on the floor with. That's a Newton's third law pair. There you have it.